When a capacitor which has some voltage V is suddenly connected to another circuit, the capacitor cannot instantly change its voltage because its voltage is generated by the charge on each plate, not by a battery or anything else in parallel with it. The capacitor retains its voltage, at least for a moment. However, as the elements in the new circuit try and change or drain or adjust the voltage in the capacitor gradually changes from its original voltage to a new voltage. Suppose that before we connected this 9-volt battery to this circuit, the capacitor had some voltage, Vc0. So we will call this the voltage at time 0, which is when we flipped the switch and connected the circuit. Let us suppose that after a very long time, t equals infinity, the capacitor reaches a different voltage, Vc at infinity. How do we determine an equation for the change in this capacitor's voltage over time? There are a few helpful facts. Number 1, the voltage in a capacitor changes according to an exponential decay rule. So there was always some kind of rule where you have e to the negative t, where t is time, over some time constant, which we call the Greek letter tau. The time constant adjusts how fast the exponential decay occurs. It's useful to note a couple things about this exponential decay. At t equals 0, this whole thing is equal to 1 when t equals 0. And at t equals infinity, this whole thing is equal to 0. So we simply need to create an equation where if t equals 0, the voltage across the capacitor is Vc at 0, and at t equals infinity, the voltage across the capacitor is Vc at infinity. Our equation is as follows. Vc at time t equals the voltage of the capacitor at infinity, or in the steady state, minus the difference in voltage between the steady state and the initial state, times e to the negative t over tau. Let's analyze this equation a little bit. When t equals 0, this whole thing is equal to 1. So we get Vc infinity minus Vc infinity, which crosses out, and then we're left with Vc0, which is going to be a positive number because this negative and this negative cancel out. So at time equals 0, Vc of t, of course, ends up being equal to Vc of 0. At t equals infinity, this term vanishes to 0, so this whole term goes away, and we're just left with Vc at infinity equals, of course, Vc at infinity. Very good. What about between t equals 0 and t equals infinity? We can think of this term, Vc infinity minus Vc0, as the difference between the original voltage of the capacitor and what the rest of the circuit wants the capacitor to be. This difference gradually decreases and fades away as t gets larger and larger until the voltage in the capacitor is basically the same as the voltage that the rest of the circuit wants the capacitor voltage to be. Let's have a concrete example with some numbers. Suppose that in this circuit, the original Vc0 was equal to 5 volts. And suppose we determined that the voltage across the capacitor at the steady state after a long time is equal to only 4 volts. Then the equation for the voltage across the capacitor would be 4 volts minus 4 volts minus 5 volts. 4 volts minus 5 volts, all times e to the negative t over tau. If we distribute in the negative sign, this is 4 volts plus 5 volts minus 4 volts times e to the negative t over tau. That is, this is equal to 4 volts plus 1 volt e to the negative t over tau. So observe that when t equals 0, this is 1 and this is 1, so the voltage at t equals 0 is 5 volts. This 1 volt represents all the extra voltage that the capacitor starts with, but this extra voltage gradually fades away. Suppose we have the opposite scenario where Vc0 equals 4 volts and Vc at infinity equals 5 volts. Then Vc equals 5 volts, the voltage at infinity, minus 5 volts minus 4 volts times e to the negative t over tau. This is equal to 5 volts minus 1 volt e to the negative t over tau. In this case, this negative 1 volt represents the voltage that the capacitor doesn't have, that it should have. The voltage that the capacitor has less than the voltage that the rest of the circuit wants it to have. The circuit wants it to have 5 volts, but it's missing a volt. However, that missingness, the lack, gradually fades away as t grows large, and finally the voltage in the capacitor grows to 5 volts. To recap, this is the equation for the voltage in a capacitor when the circuit that the capacitor is in suddenly changes. We know about what this means and what this means. We have yet to determine what tau is. I will show you how to determine these in the next video. Note that in the case of an inductor, where current instead of voltage is what is maintained, this entire equation can be written for an inductor in terms of current instead. That equation is shown here. IL is for the inductor. Observe these are all L's. They may look a little like C's, but that's because of this program, which makes my L's look curvier than they should. Angry. Note that these equations only hold for the current through an inductor or the voltage through a capacitor, not vice versa. There's no similar equation for the current of a capacitor or the voltage of an inductor. Those are different things. The voltage across a capacitor is maintained. The current across an inductor is maintained when the circuit suddenly switches. And these equations represent how that maintenance fades away.